You know, I want to begin with what might be the strangest sentence I've ever uttered in my entire career as a physicist. There is, it seems, a process at work in the universe that consumes black holes, that eats them. That takes the most voracious, most inescapable, most absolute objects we know of, objects whose entire identity is built around the simple, terrifying fact that nothing, not even light itself, can ever escape them, and slowly, patiently, relentlessly makes them disappear. Now, I want you to sit with how peculiar that is. I mean, really sit with it. Because for most of you, and for most of human history, the black hole has stood as the ultimate symbol of permanence and of doom. It is the cosmic Roach Motel, you know, the place where things check in but never check out. It is the one-way door, the point of no return, the end of all journeys. We teach it that way in our classrooms, we talk about it that way in our documentaries, and we do so for very good reasons, reasons grounded in Einstein's general theory of relativity, our deepest and most beautiful description of gravity. A black hole is a region of space-time where gravity has become so extreme, so overwhelming, that the velocity you would need to escape it exceeds the speed of light. And since nothing can travel faster than light, nothing can escape. Once you cross the boundary we call the event horizon, your fate is sealed completely, irrevocably. You will inevitably be drawn toward the center. There is no force, no rocket, no clever trick of engineering, no last-minute reprieve that can save you. The black hole holds you. It holds you forever. So how, then, can I possibly stand here and tell you that something is eating black holes, that they are vanishing, that this process is, in the language of our title today, spreading across the entire universe, and that nothing at all can stop it? Well, here's the thing, and this is what I find so wonderful about this whole story. The tale I'm about to tell you is one of the most beautiful in all of modern physics because it sits at the precise intersection of the two greatest theories that humanity has ever produced. On the one side, we have general relativity, Einstein's magnificent description of gravity, space, and time, which governs the very large, the planets, the stars, the galaxies, and, yes, the black holes. On the other side, we have quantum mechanics, the bizarre, the wonderful, the almost unbelievable set of rules that governs the very small, the atoms, the electrons, the photons, the entire subatomic realm. These two theories are taken individually, the most precisely tested and the most stunningly successful theories in the history of science. We have verified their predictions to, 10, 11, 12 decimal places in some cases. They work. They really, really work. And yet they are famously incompatible with each other. They don't get along. They're like two brilliant people who each speak a language the other cannot understand. When you try to force them together, when you try to make them describe the same situation at the same time, you get nonsense. You get infinities. You get mathematical chaos, equations that spit out answers like infinity where you expected a nice, sensible number. For nearly a century now, reconciling these two theories has been the great, unfinished project of theoretical physics, the holy grail, the thing we are all, in one way or another, chasing. But there is one place, one specific arena, one single battlefield in the entire cosmos where these two titanic theories are forced to confront each other directly, face to face, with nowhere to hide. And that place is the edge of a black hole, the event horizon, the boundary itself, because right there, at that knife's edge, between the inside and the outside, you have gravity at its most extreme, the domain of general relativity, and you have the tiny flickering quantum processes that quantum mechanics insists are happening everywhere, all the time. The two theories meet at the horizon, and they have to somehow come to terms. And when the brilliant The truly singular physicist Stephen Hawking did exactly that when, back in the early 1970s, he took the rules of quantum mechanics and carefully, rigorously applied them to the region just outside a black hole's event horizon. He discovered something that shocked the entire physics community to its core. Something that, even he himself initially found almost impossible to believe. He spent months trying to prove himself wrong, trying to find the error, before he finally accepted what the mathematics was screaming at him. He discovered that black holes are not, in fact, entirely black. He discovered that they glow ever so faintly, ever so slowly. They emit radiation. A gentle, persistent, whisper-quiet stream of particles flowing outward from the very brink of the abyss. And in emitting that radiation, they lose energy. And since, as Einstein taught us, in what is surely the most famous equation in all of science, E equals mc squared, energy and mass are simply two faces of the same fundamental coin, well, losing energy means losing mass. And losing mass means the black hole shrinks. It gets smaller. It diminishes. And if you wait long enough, and I mean a truly, almost incomprehensibly, mind-shatteringly long time, the black hole will shrink away to nothing. It will evaporate. It will, in one final brilliant flash, disappear entirely from the cosmos. This is the process. This is the thing that is eating black holes across the universe. We call it Hawking radiation, in honor of the man who discovered it. And it is, I think, without exaggeration, one of the most profound discoveries of the 20th century because it reveals a deep and utterly unexpected unity in the laws of nature. It tells us that even the most absolute, the most permanent seeming objects in all of creation are subject to the slow, patient erosion of quantum mechanics. That even black holes are, in the deepest and truest sense, mortal. They are born, they live, and they die, just like everything else, just like the stars, just like us. Now, I want to be very careful here and very honest with you because this is a topic where the popular imagination sometimes, runs a little ahead of the actual science, and I think you deserve the real picture, not a cartoon. When I say that something is eating black holes, I do not mean that there is some external entity, some cosmic predator, some great galactic beast hunting them down and devouring them. No, the process is entirely internal. It is intrinsic. It is a consequence of the black hole's own nature interacting with the quantum vacuum that surrounds it, and I'll explain exactly what that means in just a moment. The black hole, in a sense, eats itself. It dissolves from the outside in using nothing but the strange quantum properties of empty space. And when I say that the process is spreading, what I mean is that it is universal. It applies to every single black hole, everywhere throughout all of cosmic time, without exception. There is no black hole anywhere in the universe that is exempt from this slow dissolution. Not the little ones, not the big ones, not the monsters at the centers of galaxies. Every one of them is, even now, subject to this process. It is spreading in the sense that it is everywhere, woven into the fabric of reality itself. And when I say that nothing can stop it, I mean that quite literally, in a way that I will make precise as we go. Once a black hole is truly left alone, with nothing more to feed on, with no more matter falling in to replenish it, its evaporation is as inevitable, as certain as anything in all of physics. The very same theory that makes the black hole an inescapable prison also, with what I can only describe as exquisite and almost poetic irony, guarantees its eventual and total destruction. The walls of the prison are made of the very material that will dissolve them. So let me take you on this journey. Let me show you, step by careful step, how this actually works, why it is true, what the evidence is, and, most importantly, what it all means for black holes, for the universe, and, in the end, for us. Because the story does not end with a single evaporating black hole, as remarkable as that is. The story, as we will see, extends all the way to the very end of time itself, to a cosmos that, in its final and almost unimaginably distant eons, will be populated by nothing but the slow, lonely, flickering deaths of the last surviving black holes. And then, by even less than that, by almost nothing at all. But to get there, to truly understand the significance of what I'm telling you, we have to start at the beginning. We have to start with a question that sounds, at first, almost laughably simple, almost childish. But a question whose answer turns out to be one of the deepest and most surprising in all of science. The question is this: what exactly is empty space? I want you to really picture it. Picture the emptiest, most perfect vacuum you can possibly conceive of. Take a box, a simple, ordinary box, and remove all the air from it. Pump out every last molecule of nitrogen, of oxygen, of everything. Then go further. Remove all the light, all the radiation, every last photon bouncing around inside. Then go further still. Cool it down, all the way down to absolute zero, the lowest possible temperature, the temperature at which, in the old classical way of thinking, all motion would utterly cease. What you have left in that box, you would naturally think, is nothing. Pure, perfect, featureless emptiness. The void, nothingness itself, captured in a box. But here is where quantum mechanics enters the story and, completely and utterly demolishes our everyday intuition. Because according to quantum theory, and this is not speculation, this is the well-tested, experimentally confirmed bedrock of modern physics, empty space is not empty at all, not even close. It is, in fact, a seething, roiling, ceaselessly active arena. It is filled with what we call quantum fields, fields that permeate all of space. And these fields are never, ever perfectly still. They cannot be. They are always fluctuating, always jittering, always trembling, with a kind of irreducible restlessness because of a fundamental principle, one of the cornerstones of all quantum physics, discovered by the great Werner Heisenberg, the famous uncertainty principle. Now, the uncertainty principle is one of those ideas that gets, tossed around a lot, often incorrectly. So let me tell you what it actually says, at least the part that matters for our story. It tells us that there are certain pairs of quantities in nature that simply cannot both be precisely defined, precisely known at the very same instant. The more sharply you pin down one, the more fuzzy and uncertain the other necessarily becomes. It's not a limitation of our measuring instruments, it's a fundamental feature of reality itself. One such pair, the one that concerns us here, is energy and time. And what this particular version of the principle tells us is genuinely astonishing. Over very, very short intervals of time, the energy contained in a region of space is not and cannot be perfectly fixed. It is allowed to fluctuate. It can, for the very briefest of moments, spontaneously borrow energy from nowhere. From the universe's own account, on credit, as it were. And here's the truly remarkable consequence of all this. That borrowed energy, snatched from nothingness for an instant, can spontaneously transform itself into particles. Real particles with mass, popping into existence out of the apparent void. Now, these aren't ordinary everyday particles that stick around and build up into atoms and molecules and tables and chairs. No, they come in pairs, always in pairs. A particle and its antiparticle, an electron and a positron, say, or, more relevant for our story, a pair of photons, particles of light. They wink into existence together, borrowing their energy from the restless vacuum, and then almost instantaneously, before the universe has time to notice the loan, they find each other again They collide, they annihilate, and they pay back every last bit of the borrowed energy. They flicker in and out of existence so quickly, so fleetingly, that we can never ever directly observe a single one of them. We call them virtual particles. And the so-called empty vacuum, the void in your imaginary box, is absolutely teeming, absolutely saturated with them. At every single point in space, at every single instant of time, these virtual pairs are ceaselessly being created and destroyed, born and annihilated, a perpetual, frantic, microscopic quantum fizz. Like the bubbles rising in a glass of champagne, but happening everywhere, all at once, all the time, in the very fabric of space itself. Empty space, it turns out, is the busiest place in the universe. And I want to stress, again, because it matters so much, this is not some flight of theoretical fancy, not some unprovable speculation dreamed up by physicists with too much time on their hands. The existence of these vacuum fluctuations has been confirmed experimentally, directly, to extraordinary precision. There is a beautiful effect predicted back in 1948 by the Dutch physicist Hendrik Casimir, and since measured in laboratories around the world, called, naturally, the Casimir effect. If you take two flat metal plates and place them extremely close together in a vacuum, I mean very close, a fraction of the width of a human hair apart, you find that they experience a tiny but very real force pushing them together. And this force arises precisely, exclusively, because of the way the two plates alter the pattern of quantum fluctuations in the space between them versus the space outside them. The plates restrict which virtual particles can exist between them, and that imbalance produces a measurable push. So we know with certainty, empty space has structure, empty space has energy. Empty space is alive, humming and crackling with quantum activity, whether we can see it directly or not. Okay. So now I want you to hold that picture firmly in your mind, the vacuum not as a barren nothingness, but as a churning sea of flickering, ephemeral, virtual particle pairs constantly being born and constantly dying. Hold that image. And now let us bring in the black hole. Let us travel in our imagination to the event horizon, that fateful boundary of no return, and let us ask a simple but profound question. What happens to these virtual particle pairs when they happen to pop into existence right there, right at the very edge of the abyss? This was Hawking's great and beautiful insight, the leap of genius. Imagine one of these virtual pairs, let's say, for concreteness, two photons springing into existence right at the event horizon, right on the boundary. Under ordinary circumstances, out in the middle of empty space, far from any black hole, they would do what they always do. Find each other within a fleeting instant, annihilate, repay their energy debt to the vacuum, and vanish without a trace. No harm done. The book's balanced. The universe none the wiser. But at the event horizon, something profoundly different becomes possible. Because the horizon is a boundary, a one-way membrane in space-time, the two members of the pair can be separated before they have a chance to reunite. One of them, say, the particle born just on the inside of the boundary, or one that drifts inward, can fall across the horizon, plunging into the black hole, lost forever. While the other one, its partner, born just on the outside or drifting outward, escapes. It flies away, out into the wider universe, free. And now, you see, we have a problem. A genuine, deep accounting problem, a crisis of cosmic bookkeeping. That pair was supposed to annihilate. The two were supposed to find each other and pay back the energy they borrowed from the vacuum, but they can't. One of them has fallen into the black hole and can never, ever return. Nothing returns from beyond the horizon. That is the whole point of a black hole. And the other one is now a real, honest-to-goodness, observable particle flying off into space. It has no partner to annihilate with. Its partner is gone, swallowed by the dark. So the energy debt cannot be repaid in the usual way. The loan has come due, and the borrower has vanished. Someone has to pay, and the only one left to foot the bill is the black hole itself. The black hole, in effect, surrenders a tiny portion of its own energy, which is to say, by Einstein's equation, a tiny portion of its own mass in order to make that escaping particle real and to balance the cosmic books. The particle that fell in actually carries negative energy from the black hole's perspective, reducing the black hole's total mass ever so slightly, while its escaping partner carries the corresponding positive energy away into the universe. The result, the net result, as seen by anyone watching from a safe distance, is that there appears to be a steady, faint trickle of particles, mostly photons, mostly very long wavelength, low energy light, streaming away from the black hole, flowing outward from a region from which supposedly nothing can ever escape. This is the Hawking radiation. The black hole appears to glow, to shine with a faint thermal light, exactly as if it were a warm object with a definite temperature, a very, very cold temperature, but a temperature nonetheless. And here is the crucial part. Every single particle that escapes in this way carries off with it a tiny, infinitesimal morsel of the black hole's mass. The black hole is paying, particle by particle, photon by photon, for the privilege of letting these escapees go free. It is, quite literally, evaporating. It is being eaten alive, one quantum fluctuation at a time, by the very vacuum of empty space that surrounds it. And I find this, almost unbearably beautiful. I really do. After all these years of thinking about it, it still takes my breath away. The thing that ultimately destroys the black hole isn't some external force, some greater power, some cosmic predator. It's the quantum nature of empty space itself, the restless fizz of the vacuum combined with the black hole's own monstrous gravity. The prison dissolves itself from the inside out, using, as I said before, the very bricks of its own walls to bring about its own destruction. There is a kind of cosmic justice in it, a symmetry that I find deeply, deeply moving. Now, I do need to add a layer of honesty here, an important subtlety, because the simple, vivid picture, I just painted one particle of the pair falling in while the other escapes, is, in all truthfulness, a kind of cartoon. A useful cartoon, a brilliant cartoon, one that Hawking himself often used to convey the essential idea to non-specialists, but a cartoon nonetheless. The fully rigorous description, the one that emerges from the actual mathematics, is considerably more subtle and, frankly, more strange. It involves the deep and tricky question of how quantum fields behave in the curved space-time around a black hole, and the remarkable fact that observers in different states of motion, one hovering far away, another falling freely toward the horizon, will fundamentally disagree about what counts as a particle and what counts as empty vacuum. What looks like empty space to one observer can look like a warm bath of particles to another. This is genuinely mind-bending stuff, and it goes to the very heart of how relativity and quantum mechanics intertwine. But the upshot, the bottom line, the thing you need to carry with you, is exactly what the cartoon suggested. The black hole radiates, it loses mass, and it slowly, inexorably evaporates away. So at this point, you might be asking a very natural, very sensible question. In fact, you should be asking it. If black holes are evaporating, if they're glowing and shrinking and dying, then why on earth haven't we ever seen one disappear? Why are there still black holes in the universe at all? Why isn't the sky full of their final explosive flashes? And this is where the time scales involved become, frankly, absurd, comically, almost offensively vast. So large that they strain the very limits of human comprehension. Here is the crucial fact about Hawking radiation, the fact that makes all the difference. The rate at which a black hole evaporates depends on its mass, but it depends on it in a way that is deeply, wonderfully counterintuitive. You might naively think that a bigger black hole, having more stuff to radiate away, would glow more brightly and evaporate faster, but it's exactly the opposite. Small black holes are hot and they evaporate quickly. Large black holes are cold and they evaporate slowly, incredibly, ploddingly, almost infinitely slowly. The temperature of a black hole, it turns out, is inversely proportional to its mass. The more massive the black hole, the lower its temperature, and the more sluggishly, the more faintly it radiates. A truly enormous black hole is so cold, so close to absolute zero, that its glow is the faintest whisper imaginable. Let me give you some actual numbers, because the numbers here are genuinely staggering, and I think it's only by confronting them directly that you can begin to feel the scale of what we're talking about. Take a black hole with the mass of our Sunday, a perfectly ordinary stellar mass black hole, the kind that forms when a massive star, many times heavier than our sun, reaches the end of its life, runs out of nuclear fuel, and collapses catastrophically under its own gravity. These are the bread and butter black holes of the cosmos, and we know of many of them. So, how long would it take for such a black hole, left entirely alone in the cold of space, to evaporate completely via Hawking radiation, to shrink away to nothing? The answer is about 10 to the 67th power years. Let me write that out for you so you can feel it. That's a 1, followed by 67 zeros, years. Now, that number means nothing to anyone. It's just a string of zeros, so let me give you something to compare it against. The current age of our universe, the time elapsed since the Big Bang, is about 14 billion years. 14 billion, which sounds like a lot, and in human terms, it is unimaginably long. But written in the same notation, 14 billion years is roughly 10 to the 10th power years. A 1 followed by just 10 zeros. So a solar mass black hole would take 10 to the 67th years to evaporate against a universe that is merely 10 to the 10th years old. The difference between those two numbers is a factor of 10 to the 57th, which means such a black hole would persist for about 10,000 trillion times the current age of the entire universe before it finally winked out. The number is so colossal, so far beyond anything in human experience, that it, essentially defies any attempt by the human mind to truly grasp it. We can write it down. We can do arithmetic with it, but we cannot feel it. It is simply too big. And that's just for a black hole the mass of our sun, which in the grand scheme of black holes is on the smaller end. For the supermassive black holes, the true behemoths that lurk at the centers of galaxies, including the one at the center of our own Milky Way with a mass of about 4 million suns, and others out there with masses of billions of suns, the timescales become even more extreme, even more absurd. We're talking about 10 to the 100th power years and beyond, a Google of years. We are talking about durations so staggeringly, so violently long, that the universe as we know it, the universe of stars and galaxies and light, will have utterly and completely transformed itself many times over before these giants even begin to noticeably shrink, before they even lose a meaningful fraction of their first percent. So this is precisely why we have never seen a stellar mass or a supermassive black hole evaporate. The process is real as anything in physics, but for the black holes we actually know about, the black holes we observe with our telescopes, it is so breathtakingly slow as to be completely, utterly negligible on any time scale we could ever hope to witness. In fact, and this is a lovely twist, today these black holes are not even shrinking at all. They are growing ever so slightly. Why? Because they are bathed, like everything else in the cosmos, in the faint afterglow of the Big Bang itself, the cosmic microwave background radiation, that ancient cooling sea of light that fills all of space. And right now, that background radiation, though it is extremely cold, just a few degrees above absolute zero, is still warmer than these enormous frigid black holes. So the black holes are absorbing more energy from that ancient light than they are losing through their own feeble Hawking radiation. The books, for now, run in their favor. They are ever so slowly gaining weight, not losing it. But, and here's the key, this is only a temporary state of affairs, a passing phase. Because the universe is expanding, and as it expands, that cosmic microwave background is continuously cooling, getting colder and colder and colder with every passing eon. Its light stretched ever longer and fainter by the relentless stretching of space itself. And eventually, in the far, far future, it will become colder than even the supermassive black holes. And at that moment, that turning point in cosmic history, the balance will finally tip. The black holes will begin, at long last, to radiate away more than they absorb. The slow eating will commence in earnest, and from that moment forward, their fate is utterly sealed. The dissolution will begin, and nothing in heaven or earth will be able to halt it or reverse it. There is, however, one special category of black hole for which this evaporation is not some impossibly distant abstraction, not some event reserved for the unimaginable future. One particular kind of black hole that could be evaporating right now, today, at this very moment, somewhere out there in the depths of the cosmos, or perhaps, who knows, even in our own galactic neighborhood. And these are the black holes that have astronomers and physicists genuinely, palpably excited. Because if we could only catch one of them in the act, in the throes of its final explosive death, we would, for the very first time in history, see Hawking radiation directly with our own instruments. We would confirm Hawking's profound and beautiful prediction, not through abstract mathematics, but through hard observation. We would witness, the actual death of a black hole. And that would be, without question, one of the great triumphs in the entire history of science. I am talking about what we call primordial black holes. And to understand them, to understand what they are and why they might be winking out of existence even as we speak, we have to journey back through all of cosmic history. All the way back to the very first fraction of a second after the Big Bang itself. Because these particular black holes were not born as the others were from the collapse of dying stars. No, these were born, if they exist at all, in the unimaginable density, the searing heat, and the violent chaos of the newborn universe in the first instance of creation. Let me explain how that could happen. The black holes that we form today from collapsing stars are all necessarily quite massive, several times the mass of the sun at the very least, because it takes a very heavy star to make one. And so, as we've seen, their evaporation timescales are absurdly, impossibly long. None of them are anywhere remotely close to dying. But in the very early universe, conditions were radically, fundamentally different. In the first tiny sliver of a second after the Big Bang, the cosmos was inconceivably dense and inconceivably hot, a roiling, churning plasma of energy and elementary particles. And it was not perfectly smooth. There were fluctuations, tiny regions here and there, where the density happened to be slightly randomly higher than average. And if one of those regions were dense enough, if the concentration of matter and energy crossed a certain critical threshold, it could have collapsed directly, then and there, in that very first instant, into a black hole. No star required, no stellar life cycle, just a pocket of the early universe folding in on itself under the sheer weight of its own density. And here is the absolutely crucial point, the thing that makes primordial black holes so special and so interesting. Because they form from these density fluctuations rather than from stars, they could have been born with an enormous range of possible masses, including very, very small ones. Some might have formed with the mass of a mountain, compressed into a region smaller than a single atom. Some might have been far smaller still, some larger. There was no minimum mass requirement, no lower limit set by the physics of stars. And here is where it gets really wonderful. If you sit down and actually do the calculation, if you work out which mass of primordial black hole would have an evaporation, lifetime almost exactly equal to the current age of the universe, you arrive at a beautiful and specific answer. A primordial black hole born with a mass of about 1 billion tons, roughly the mass of a large mountain or a good-sized asteroid, but crushed down into a space smaller than a proton, would have an evaporation lifetime of approximately 14 billion years, which is to say, the current age of the universe. Do you see the staggering implication of that? Do you feel it? A primordial black hole of that one particular special mass, if it formed in the chaos of the Big Bang nearly 14 billion years ago, would be finishing its evaporation right now, in our cosmic era. In our time, it would have spent the entire age of the universe slowly, patiently radiating itself away, and it would be reaching in these very years the final catastrophic explosive moment of its death. The grand finale after a 14 billion year performance. And the burst of radiation from that death, a flash of high energy gamma rays, could in principle be detectable by our telescopes here on Earth. And that is precisely where our story takes its next dramatic turn. Because the death of a small black hole, as we are about to see, is not a quiet, gentle, peaceful fading into the dark. Oh no, it is not a whimper. It is in fact one of the most violent, most spectacular, most explosive events that the laws of physics permit, a fireworks display unlike any other in the cosmos. Now, before we go on to that grand finale, I want to take just a few minutes to tell you a bit more about how this discovery actually came about. Because the history is, every bit as fascinating as the physics itself, and it reveals something important about how science truly works. Because Hawking did not arrive at his radiation out of nowhere. He arrived at it by way of one of the most surprising and beautiful connections in all of physics, a connection between black holes and the seemingly unrelated science of heat, of thermodynamics. Let me back up a little. In the years before Hawking's great discovery, physicists studying black holes had noticed something rather curious. A young researcher named Jacob Bekenstein, then a graduate student at Princeton, had been thinking hard about a deep puzzle. The puzzle was this. There is a sacred fundamental law in physics called the second law of thermodynamics. And what it says, in essence, is that the disorder of the universe, a quantity we call entropy, can only ever increase. It never decreases. You can scramble an egg, but you can never unscramble it. You can shatter a glass, but the pieces will never spontaneously leap back together. Heat flows from hot to cold, never the reverse, of its own accord. Disorder always wins in the end. This is one of the most ironclad, most inviolable laws in all of science. The whole arrow of time, the very distinction between past and future, is bound up in it. But black holes seem to threaten this sacred law because, you see, if you take some hot gas, some disordered, high entropy stuff, and you simply throw it into a black hole, then poof, it's gone, vanished behind the horizon. And so the entropy of the outside universe would seem to have decreased. You would have, in effect, a cosmic trash can into which you could throw all the disorder of the universe, hiding it away forever, and thereby violate the second law. And that, to physicists, was deeply, deeply troubling. Unacceptable, even. Because the second law is not the kind of thing you give up lightly. Bekenstein had a radical, almost heretical idea. What if, he proposed, the black hole itself has entropy? What if, when you throw your hot gas into the black hole, the entropy doesn't vanish at all, but is instead added to the black hole so that the total entropy, the entropy outside plus the entropy of the black hole never goes down? And he made a specific, bold proposal that the entropy of a black hole is proportional not to its volume, as you might naively expect, but to the area of its event horizon. The bigger the surface of the black hole, the more entropy, the more hidden disorder it contains. As things fall in, the black hole grows, its surface area grows, and its entropy grows right along with it, enough, always enough, to balance the books and save the second law. It was a beautiful idea, but it had what seemed at first to be a fatal flaw, a killer problem. Because here is a basic, unavoidable truth of thermodynamics. Anything that has entropy, anything that has a temperature, must radiate. It must glow. That's just what hot things do. A hot poker glows red, the sun glows brilliant white. Even you and I glow faintly in the infrared. If a black hole has entropy, and therefore a temperature, then it must emit radiation. But everyone knew, everyone was absolutely certain that black holes cannot emit anything at all. Nothing escapes a black hole. That is the very definition of the thing. So Bekenstein's idea seemed self-contradictory, and many of the leading physicists of the day, including at first Stephen Hawking himself, were quite sure he was simply wrong. And here is the wonderful twist, the turn that makes this such a great story. Hawking set out, initially, to prove Bekenstein wrong, to demolish this troublesome idea once and for all. He took the full machinery of quantum mechanics and applied it with great care and rigor to the space around a black hole, fully expecting to show that black holes emit nothing, that they have no temperature, that Bekenstein's entropy idea must therefore be mistaken. But the mathematics, had other plans. The mathematics refused to cooperate. Instead of showing that black holes emit nothing, Hawking's own calculations showed, undeniably, that they do emit radiation, that they do have a temperature, that Bekenstein, the audacious graduate student, had been right all along. Hawking had set out to bury the idea, and instead he ended up providing its deepest and most rigorous proof. He must have been, I imagine, utterly astonished. And to his enormous credit, he followed the mathematics where it led, even though it overturned his own expectations. That is science at its very finest, the willingness to be proven wrong by the universe itself. And the connection ran even deeper than anyone had dreamed. It turned out that the entire framework of black hole physics could be rewritten in the language of thermodynamics. There emerged what we now call the 4 laws of black hole thermodynamics, which mirror with uncanny precision the 4 laws of ordinary thermodynamics that govern steam engines and refrigerators and chemical reactions. The mass of a black hole plays the role of energy. The surface gravity at its horizon plays the role of temperature. The area of its horizon plays the role of entropy. It was as though black holes, these creatures of pure gravity, were secretly, deep down, thermodynamic objects governed by the same laws as a cup of hot coffee cooling on your desk. And nobody had expected that. Nobody. The connection between gravity, quantum mechanics, and heat that emerged from this work is, I think, one of the most profound hints we have about the ultimate unified nature of physical law. It is a clue, a tantalizing, glittering clue left for us by the universe, pointing toward some deeper theory we have not yet fully grasped. So when we talk about a black hole's temperature, we are not speaking loosely, not using a mere metaphor. We mean it precisely, literally, mathematically. A black hole with the mass of our sun has a temperature of about 60 billionths of a degree above absolute zero. Unimaginably cold, far, far colder than the depths of intergalactic space, far colder than anything that exists naturally in the universe today. And that frigid temperature is exactly why such a black hole radiates so feebly, why it takes those 10 to the 67th years to evaporate. But a much smaller black hole, one of our primordial ones, say with the mass of a mountain crushed into the size of a proton, would be searingly, blazingly hot. Hot enough to glow fiercely in gamma rays, the most energetic form of light there is. And the very smallest black holes, in their final moments, reach temperatures of trillions upon trillions of degrees. Which brings us, you see, right back to the explosive death I keep promising you, but I want to dwell just a moment longer on what all of this means, because I think it's easy to let these ideas wash over you without truly registering how revolutionary they are. Think about what we've just learned. We've learned that a black hole is not a simple featureless object. It is not just a bottomless pit. It is a thermodynamic system with a temperature and an entropy. And that entropy is the largest entropy that can possibly be packed into a given region of space. In fact, and this is genuinely staggering, a black hole contains the maximum possible amount of entropy, of hidden information, that any object of its size could possibly contain. Nothing in the universe is more disordered, more information-rich per unit of surface area than a black hole. And the entropy is proportional to the surface area, the two-dimensional boundary, not the three-dimensional volume inside. That single strange fact that the information content of a black hole lives on its surface, not in its interior, would go on decades later to inspire one of the most mind-bending ideas in all of theoretical physics, the so-called holographic principle, which suggests that the entire three-dimensional universe might, in some deep sense, be encoded on a distant two-dimensional surface, like a cosmic hologram. But that is a story for another day, perhaps. I mention it only so you can see how a single thread, the entropy of a black hole, runs through and connects so many of the deepest questions we have about the nature of reality. Pull on that one thread, and the whole tapestry of modern physics begins to move. So let me pause here, just for a moment, at the very edge of this idea, and let it all settle in your mind before we plunge ahead. We have established the central, the astonishing, the almost paradoxical fact at the heart of our whole story: black holes are not eternal. They're not the permanent, unchanging, absolute prisons of our imagination. They radiate, they shrink, they die. The most permanent seeming objects in the entire universe are, in the deepest and most fundamental sense, temporary, fleeting, mortal. And the agent of their destruction, the thing that eats them, is woven into the very fabric of empty space itself, into the irreducible quantum restlessness of reality. It is universal, it is relentless, it is patient beyond all imagining. And once it truly takes hold, once a black hole is left alone to face the slow erosion of the vacuum, nothing at all can stop it. In just a moment, I want to show you what happens at the very end. When a black hole has shrunk down to its final frantic moments, when the gentle trickle of radiation becomes a roaring torrent, and then, in a final instant, an explosion of almost unbelievable violence, I want to tell you about the great cosmic hunt that is underway right now to find these dying primordial black holes, and about what extraordinary things we might learn if we ever succeed in catching one. And then, after that, I want to take you on the longest journey of all, forward all the way to the end of time, to a universe of almost infinite age, where the last black holes flicker out one by one, and the cosmos passes into its final dark and strangely, profoundly peaceful era. The age after the lights go out. But before we get there, let me leave you with one image to carry into the next part of our story. I want you to picture, just for a moment, the sheer audacity of what we've done here as a species. A few centuries ago, we did not even know that other galaxies existed. A century ago, we did not know that the universe was expanding or that it had a beginning. 50 years ago, we did not know that black holes radiate, and here we are, sitting on a small planet, orbiting an ordinary star, having worked out through nothing more than careful observation, patient reasoning, and the strange and beautiful language of mathematics, that the most powerful objects in all of creation are slowly, inevitably dissolving back into the quantum foam from which everything came. We figured this out with our minds. That, ought to give us pause. It ought to fill us with a certain wonder, not just at the universe, but at our own peculiar capacity to comprehend it. And it is precisely that capacity, that improbable gift of understanding, that I want to return to again and again as our story unfolds. Because in the end, I think it may be the most remarkable part of the whole tale. So, with all of that ahead of us, with the death of black holes and the death of the universe itself still to come, so we'd arrived at this genuinely startling, almost vertiginous conclusion: black holes evaporate. They radiate their very mass away into the quantum vacuum, slowly at first, agonizingly slowly, and the time scales for the great ones are so vast as to be almost entirely meaningless to the human mind. But I ended by hinting at something else, didn't I? At a special class of black holes that might be dying right now in our own cosmic moment. And at the fact that the death of a black hole, when at last it comes, is not a gentle thing at all, but something far more violent, far more spectacular. So let's pick up right there, at the dramatic and explosive end of a black hole's long, long life. Here is the key idea, the crucial mechanism that makes the ending so violent. I told you back in part 1 that the temperature of a black hole is inversely proportional to its mass. The smaller it gets, the hotter it gets. Now, I want you to really think carefully about what that implies as a black hole evaporates. As it slowly loses mass to Hawking radiation, it gets smaller, and as it gets smaller, it gets hotter, and as it gets hotter, it radiates more furiously, more energetically, and radiating more furiously means it loses mass even faster than before, which makes it smaller still, which makes it hotter still, which makes it radiate yet more violently, which makes it lose mass faster yet. Do you see what's happening here? Do you feel the trap closing? It's a runaway process, a feedback loop, a vicious spiral that accelerates without limit, feeding on itself, building on itself faster and faster and faster. For almost the entire near eternal life of a black hole, for those 10 to the 67th years or more, the evaporation is so slow as to be utterly imperceptible, a frigid object barely managing to whisper the occasional photon into the surrounding dark. But in the final stretch, in the last chapter of its existence, the process spirals completely out of control. The black hole heats up catastrophically. The temperature climbs toward the infinite. The gentle trickle of radiation becomes a stream, the stream becomes a flood, the flood becomes a raging torrent, and then, in the very last instant, the black hole detonates. It explodes in an enormous, brilliant, final burst of high-energy radiation, gamma rays, and particles of every conceivable kind, electrons and positrons and quarks and neutrinos, a last violent spray of everything as the final remnant of its mass is converted all at once into a flash of pure energy. The numbers here are, once again, quite something. In its very last second of life, a dying black hole releases energy equivalent to billions upon billions of 1 megaton hydrogen bombs, all detonating at once. The entire remaining mass goes up in a single instant, in a flash of gamma rays so intense that it could, in principle, be detected across truly enormous cosmic distances. So the death of a black hole is not, after all, a fading ember slowly going cold. It is the precise opposite. It is a fireworks finale of unimaginable grandeur, a blazing, explosive, triumphant end to an object that may have existed quietly and patiently since very nearly the dawn of time itself. The black hole spends an eternity in cold and silent darkness, and then departs the universe in a final, glorious blaze of light. And this, you see, brings us right back to those primordial black holes I introduced you to. Let me now explain in a bit more depth why they matter so enormously to this whole story, why they are, in a sense, our one great hope of actually witnessing this process with our own instruments. The black holes that form today in the modern universe from the collapse of dying stars are all, as we've established, quite massive, several times the mass of the Sun at the very minimum. Their evaporation timescales are absurdly, hopelessly long, far longer than the current age of the cosmos, so not a single one of them is anywhere remotely close to its explosive death. They are all still in the cold, quiet, near eternal middle of their lives. We will not catch any of them dying. Not us, not our descendants, not any conceivable civilization for an almost limitless span of future time. But the primordial black holes are different, radically different, because they could have formed in the chaos of the early universe with a whole spectrum of different masses. And as I showed you, a primordial black hole born with a mass of about 1 billion tons, the mass of a mountain, would have an evaporation lifetime of right around 14 billion years, the current age of the universe. So such a black hole, formed in the first instant after the Big Bang, would be reaching the end of its life, the explosive grand finale, right now, in our era. And one born slightly heavier would still have a little ways to go, while one born slightly lighter would have already exploded long ago in the universe's distant past. So there is, at this very moment, a genuine and serious scientific hunt underway, a search across the heavens for these final explosions. Astronomers using gamma-ray observatories, instruments like the Fermi Gamma-Ray Space Telescope orbiting high above the Earth, and great arrays of detectors on the ground designed to catch the faint flashes of high-energy radiation cascading through our atmosphere, are scanning the skies, watching, waiting for the characteristic signature of an evaporating black hole's last gasp. And it would be a very particular signature, a sudden, brief, intensely energetic burst of gamma rays with a very specific spectrum, a very specific pattern of energies that would distinguish it from all the other violent and dramatic events that fill the cosmos, from the supernova explosions of dying stars, from the catastrophic collisions of neutron stars, from all the other fireworks of the universe. The death of a black hole would have its own unmistakable fingerprint, and we are looking for it. Now, I want to be completely honest with you, as I always try to be, because I think honesty is the very soul of science. We have not yet detected such an event, not definitively, not in a way that everyone agrees upon. The searches have thus far come up empty, or at best inconclusive. We have not yet seen a black hole die. But, and this is important, this is a point that I think is often misunderstood about how science works, this is not a failure. Far from it. Even the absence of a detection is enormously, genuinely valuable because it places limits, real and quantitative limits, on how many of these primordial black holes can possibly exist out there. You see, if the universe were absolutely teeming with them, if they were as common as, say, ordinary stars, then we would expect to see their explosions happening regularly all over the sky all the time. And we don't. We see none. So we can conclude with real confidence that primordial black holes of this particular critical mass must be relatively rare. They cannot make up more than a certain small fraction of the matter in our cosmic neighborhood. And that conclusion, that limit, in turn tells us something precious and otherwise inaccessible about the conditions in the very early universe, about the nature and the size of those primordial density fluctuations from which these black holes would have formed. This is, how science so often actually proceeds. Not always through triumphant discovery, through the dramatic eureka moment, but through the slow, patient, careful process of ruling things out, of narrowing the possibilities, of saying with ever greater precision, the universe is not like this and it is not like that, and so it must be somewhere within these remaining bounds. Every search that comes up empty sharpens our understanding, refines our models, tightens the constraints. And so the hunt continues, year after year, with ever more sensitive instruments, because the prize, the potential payoff, is simply so extraordinary. If we ever do catch one of these explosions, if we ever do see, even once, the death flash of a black hole, it would be a monumental, era-defining confirmation of Hawking's theory. It would be direct, hard, observational proof that black holes truly do radiate, that they truly do evaporate, that they truly do die. It would unite in a single observed event the realm of the very large and the realm of the very small, gravity and the quantum, the two great pillars of physics that have stood apart for so long. It would be, I think without exaggeration, one of the very greatest triumphs in the entire history of human thought. Let me dwell for just a moment on what that final moment would actually look like, because I think the details are genuinely worth picturing. When a primordial black hole reaches the last stages of its evaporation, the last few hours, then the last few minutes, then the last few seconds, the radiation it pours out climbs the energy ladder. It begins by emitting low-energy photons. Then, as it heats up higher and higher energy particles, first electrons and positrons, then as the temperature soars to truly astronomical values, heavier and heavier particles, quarks and gluons, spraying out in a furious shower. In the final second, the black hole would be radiating at a temperature of trillions of degrees, far hotter than the center of any star, far hotter than the universe itself was even a tiny fraction of a second after the Big Bang. And then, in the last instant, it would all be over a final burst, a flash, and then nothing. The black hole would be gone, leaving behind only an expanding shell of high-energy particles racing outward through space, and an empty patch where a moment before one of the oldest objects in the universe had existed. Now, what would we actually see here on Earth if such an event happened, say, somewhere in our galaxy? We would not, of course, see it with our eyes. The radiation would be in gamma rays, far beyond the range of human vision, but our instruments would catch it. We would record a sudden, brief, intense spike of gamma rays lasting perhaps a fraction of a second with that very particular spectrum I mentioned, a spectrum that climbs toward higher energies in exactly the way Hawking's theory predicts, a fingerprint quite unlike anything produced by other cosmic events. If we saw that signature even once and could confirm it, the implications would be staggering. We would have, for the first time, direct experimental proof of a process that unites quantum mechanics and gravity. We would have confirmed that black holes truly are thermodynamic objects. We would have witnessed with our own machines the death of one of the universe's most ancient inhabitants. It is, in my view, one of the great experimental prizes still out there waiting to be claimed. And the fact that it might happen at any moment, that tonight or next year or a decade from now, one of these ancient black holes might reach the end of its long life and announce its death to our waiting detectors is, a genuinely thrilling thought. And there is yet another reason, a quite separate reason, why these primordial black holes are so deeply fascinating to physicists, a reason that connects them to one of the very greatest unsolved mysteries in all of cosmology. You may well have heard of dark matter. It is one of the strangest and most profound puzzles we face. When we look out at the universe, at the way galaxies rotate, at the way they cluster together, at the way light bends as it travels across the cosmos, we find over and over again overwhelming evidence that there is far, far more matter out there than we can actually see. Something like 85% of all the matter in the universe appears to be invisible, dark. It emits no light, it absorbs no light, it neither shines nor reflects nor glows. We detect it only exclusively through the pull of its gravity, through the way it shapes and holds together the great structures of the cosmos. Without it, galaxies would simply fly apart. They spin too fast to hold themselves together with their visible matter alone. So we know it's there. We're quite certain of that. But we have absolutely no idea, no confirmed idea, what it actually is. It is one of the biggest open questions in all of science. And one intriguing possibility, an idea that has gone in and out of fashion over the decades, but that has been seriously, vigorously revived in just the past several years, is that some, or perhaps even all, of this mysterious dark matter could be made of primordial black holes. Not the ones that are evaporating right now. Those, as we've seen, are too small and too rare to account for much. But primordial black holes in a different mass range. Ones massive enough to persist, to survive for the full age of the universe without evaporating, yet small enough and dark enough to have so far escaped all our direct attempts to detect them. They could be out there, right now, in untold numbers, drifting silently through the vast halos of galaxies, threading invisibly through the space between the stars, making up the hidden scaffolding of mass that shapes the entire structure of the cosmos. Black holes as the dark matter. It's a striking, almost poetic idea that the invisible majority of the universe might be composed of the collapsed remnants of the Big Bang itself. Now, this idea has, as I say, gone in and out of favor. Various observations have placed strong constraints on it, ruling out certain mass ranges, narrowing the windows of possibility where such black holes could hide. If there were too many black holes of certain masses, we would see their gravitational effects in ways we don't observe. They would distort the light of distant stars too often, or disrupt delicate structures, or leave other fingerprints we simply don't find. So the idea is hemmed in, constrained, but it has not been ruled out. There remain windows, ranges of mass, where primordial black holes could still, in principle, account for the dark matter. And it remains a genuinely tantalizing option, one that ties the physics of Hawking radiation directly to the grandest questions about what the universe is fundamentally made of. Because, you see, to know whether primordial black holes can be the dark matter, you have to understand precisely how they evaporate, which ones survive to the present day, which ones have already died, and what fingerprints their deaths would leave behind. And so the slow eating of black holes by the quantum vacuum becomes, in this context, not just a curiosity, but an essential tool for understanding the very composition of reality. Everything connects. That is one of the deep lessons of physics. Pull on any one thread, and you find it woven into all the others. But let me now step back from the observational hunt, from telescopes and dark matter and the search of the skies, and return to something more conceptual, something deeper. Because lurking within this whole idea of black hole evaporation, hidden inside it like a seed, there is one of the most profound and genuinely troubling puzzles in all of theoretical physics. A puzzle so deep, so stubborn, that it occupied Stephen Hawking and many of the very greatest minds in physics for the better part of 40 years. A puzzle that, in some real sense, is still not completely resolved even today, even now. It goes by the name of the black hole information paradox. And I want to walk you through it carefully, step by step, because I think it's one of the most beautiful intellectual puzzles ever posed, and understanding it will take you very close to the frontier of what we currently know about the universe. Here is the issue. Let me build it up slowly. In physics, in quantum mechanics specifically, there is a deeply held, almost sacred principle that information is never, ever truly lost, never destroyed. Now, what do I mean by information? I mean the complete and total description of a physical system, the positions, the velocities, the properties, the quantum states of every particle that makes it up. All the details that specify exactly and completely what something is and how it came to be. And the principle which flows from the very heart of quantum theory says this: if you know the complete quantum state of a system at one moment in time, then you can, in principle, using the fundamental laws of physics, determine its complete state at any other moment, whether in the future or in the past. The underlying laws are what we call reversible. They run equally well forwards and backwards. Nothing is ever genuinely erased from the universe. The information may get scrambled, dispersed, hidden, mangled beyond all practical hope of recovery, but it is always, in principle, still there. Always preserved. The universe never truly forgets. Let me give you the classic illustration, because it makes the idea concrete. Think of burning a book. You toss a book into a fire, and you watch it burn. The pages curl and blacken, they turn to ash and smoke, the words seem to vanish into the flames. It certainly looks to all the world as though the information in that book, the words, the sentences, the ideas, has been utterly and permanently destroyed, gone forever. But according to the deepest principles of physics, that is not actually so. In principle, and I stress, in principle, not in any way we could ever practically manage, if you could track every single particle of the smoke, every fleck of the ash, every photon of light emitted by the fire, every tiny vibration imparted to the surrounding air, and if you knew the laws of physics with perfect precision, then you could run the whole process backwards in your calculations and reconstruct exactly every word that had been written on every page. The information was not destroyed. It was merely scrambled. dispersed into an unimaginably complex pattern of smoke and heat and light, made hopelessly, absurdly impractical to recover, but not, in the deepest and most fundamental sense, gone. It is still there, encoded in the fine details of the radiation and the ash. The universe still, in principle, remembers the book. Okay? So now, hold that principle firmly in mind. Information is never truly lost, only scrambled, and let us perform a different experiment. Instead of burning our book, let us throw it into a black hole. The book sails across the event horizon and is lost completely and forever to the outside world. Fine. So far, no problem. The information in the book is now inside the black hole. It's still preserved, we'd say, just hidden away behind the horizon, locked in the vault, inaccessible but not destroyed. The books, as it were, still balance, but now, and here is the crux, here is where the whole thing comes crashing down. The black hole slowly evaporates. Through Hawking radiation, over those vast eons, it shrinks and shrinks until finally it is gone entirely. It has vanished. And in Hawking's original foundational calculation, the radiation that comes pouring out during this evaporation is purely thermal, which is to say it is completely random, featureless. It carries no information whatsoever about the particular things that fell into the black hole. The Hawking radiation depends only on the black hole's total mass and a couple of other gross properties like its spin and charge, and absolutely nothing else. It does not care, it does not know whether you threw in a book or a brick or a chunk of antimatter or an encyclopedia or a grand piano. The radiation that emerges is the same featureless random hiss regardless. So here is the terrible question, the paradox in its full and naked form. When the black hole has finished evaporating and has utterly disappeared from the universe, where did the information in the book go? It cannot be inside the black hole because there is no black hole anymore, it's gone. And it cannot be in the radiation because the radiation, by Hawking's own calculation, was random, thermal, featureless. It carried no information at all. So it seems, inescapably, that the information has been truly, permanently, irrevocably destroyed, erased from reality. And that, you see, would be an absolute catastrophe for physics, because it would violate that sacred, fundamental principle of quantum mechanics that information is never lost. It would mean that the laws of physics are not, after all, reversible. It would mean that the past cannot be reconstructed from the present. It would mean, in a deep sense, that the universe can genuinely forget. And if that were true, the entire logical structure of quantum mechanics, the most successful theory in the history of science, would be threatened at its very foundation. This is the information paradox. And I want to be very clear that it is not some minor technical quibble, not some footnote that only specialists could care about. It is a genuine head-on collision between our two great theories. General relativity, through Hawking's calculation, says the information should be lost. Quantum mechanics says it absolutely cannot be. Two of the most rigorously tested, most magnificently successful theories in all of science, pointing in flatly opposite directions, contradicting one another at the most fundamental level. And that, is exactly the kind of contradiction that physicists live for. Because it means that one of our theories, or perhaps both, must be incomplete. It means there is something deep we do not yet understand. And lurking in that gap, in that contradiction, there is almost certainly a profound new truth waiting to be discovered. For a long time, Hawking himself believed that the information was truly lost. That black holes represented a genuine, fundamental breakdown of quantum predictability, that the universe really could forget, that this was simply a new feature of reality we had to accept. He held this position for years, and he argued it forcefully. He even famously made a formal bet with two other prominent physicists, John Preskill and Kip Thorne, over the question Hawking and Thorne betting that information is destroyed, Preskill betting that it is preserved. The stakes, as I recall, were an encyclopedia from which, fittingly, information can always be freely retrieved. But over the following decades, the tide of opinion within physics slowly, steadily turned through a remarkable series of deep theoretical developments, many of them emerging from string theory and from the study of that extraordinary mathematical relationship I mentioned earlier. The holographic principle physicists gradually came to believe that the information is in fact preserved after all, that it must somehow be encoded in the Hawking radiation, hidden in subtle correlations, delicate patterns, and entanglements between the outgoing particles that Hawking's original calculation had been simply too crude, too approximate to capture. The radiation, in this newer and deeper understanding, is not perfectly thermal and random after all. It only looks that way if you examine it superficially. Hidden within it, in immensely scrambled but ultimately recoverable form, is the imprint of everything that ever fell in. The book is not destroyed. Its information leaks back out agonizingly slowly, encoded in the faint patterns of the escaping radiation over the entire vast lifetime of the black hole. And in 2004, Stephen Hawking himself publicly conceded the bet. He stood up at a major scientific conference and acknowledged that he now believed information is preserved, and he presented John Preskill with a baseball encyclopedia from which information can be retrieved at will. It was a remarkable moment, one of the world's greatest physicists publicly changing his mind in front of his peers because the weight of evidence and argument had shifted. Again, that is science at its noblest. Now, I will be candid with you. The precise details of exactly how the information escapes are still being worked out even now. This is, at this very moment, today, one of the most active and exciting frontiers in all of theoretical physics. In just the past few years, there have been genuinely remarkable breakthroughs, new calculations involving exotic and almost unbelievable geometric structures, including microscopic wormholes that appear in the mathematics, connecting different regions of space-time, and new and powerful ways of understanding precisely how and when the information leaks out over the course of a black hole's evaporation. We are getting closer to a complete and satisfying answer than we have ever been. But we are not entirely, finally there yet. The puzzle is not fully solved. And what I find so beautiful about all of this, so genuinely thrilling, is that the humble process of black hole evaporation, this slow eating away by quantum effects that I've been describing to you, has become one of our single most important windows into the ultimate goal of all theoretical physics, the grand prize, a complete, unified theory of quantum gravity, a theory that would at long last reconcile Einstein's gravity with the quantum world, that would heal the great rift at the heart of physics. The dying black hole, you see, is not just a cosmic curiosity. It is a laboratory for the very deepest laws of nature. By understanding how black holes die, we are, in a sense, trying to read the final and most fundamental pages of the book of the universe. There is one more conceptual point I want to make before we leave the information paradox behind, because I think it connects to something very deep about the nature of time itself. Remember the second law of thermodynamics, which I told you about back in part 1, the law that says entropy, disorder, always increases. Well, when a black hole evaporates, something rather profound happens to the entropy of the universe. The enormous entropy that was locked up in the black hole, and remember, a black hole holds the maximum possible entropy for its size, gets converted over the course of the evaporation into the entropy of the outgoing Hawking radiation, spread across a vast volume of space. And it turns out that the radiation carries even more entropy than the black hole did. So the total entropy of the universe still increases just as the second law demands. The evaporation of a black hole is, in this sense, a perfectly ordinary thermodynamic process obeying the same law as a melting ice cube or a cooling cup of coffee. The arrow of time points in the same direction for a dying black hole as it does for everything else. And I find that reassuring in a way that even at the most extreme frontier of physics, where gravity and quantum mechanics collide, the humble, universal law of increasing entropy still holds sway. The same law that governs your morning coffee governs the death of black holes and the fate of the cosmos. There is a unity there, a consistency that runs from the kitchen table all the way to the end of time. But now I want to take you somewhere else entirely. I want to take you forward in time, way, way, way forward, further than we have yet dared to go in this conversation. Because the evaporation of black holes is not merely an isolated curiosity, not just a strange fact about a strange kind of object. It is a central and decisive chapter in the ultimate story of the universe itself. The story of how absolutely everything ends, the final fate of all things. And black hole evaporation, it turns out, plays the leading role in the last act of that cosmic drama. We live, in what cosmologists sometimes call the stelliferous era, the age of stars. And it is a glorious time to be alive, cosmically speaking. The universe right now is full of bright, blazing galaxies glittering with the light of hundreds of billions of stars apiece. New stars are constantly being born, igniting in vast, beautiful clouds of collapsing gas. Old stars are dying, some of them in spectacular supernova explosions that briefly outshine entire galaxies. There is light everywhere, there is warmth, there is structure and activity and drama and change. It is a vibrant, luminous, restless, living cosmos. But this era, as grand and as permanent as it feels to us, as eternal as the night sky may seem this era is, in truth, merely a brief and fleeting opening act in the immense, almost endless lifespan of the universe. A short, bright flash near the very beginning of a story that stretches on and on and on into almost inconceivable depths of future time. And it will not last. The age of stars will end. Why? Why must it end? Because stars require fuel. They shine by fusing hydrogen and helium in their cores, and the universe contains only a finite, limited supply of that fuel. It is being steadily consumed, locked away, used up, and eventually, in something like 100 trillion years, which is already vastly longer than the current age of the universe, the gas will run too thin. The raw material for new stars will be exhausted. The last stars will form, will burn through their fuel as all stars do, and will die, and no new ones will rise to take their place. One by one, across 100 billion galaxies, the lights will go out. The brilliant, glorious light of the stelliferous era will fade star by star by star until at last the cosmos is plunged into a deep and universal darkness. The age of stars will be over forever. And what comes next, we call the degenerate era, an age populated not by shining stars but by their cold, dark, dead remnants, white dwarfs, slowly cooling toward absolute zero. Neutron stars frozen and silent, and black holes scattered like dark seeds throughout the dim and dying galaxies. The lights across the entire universe will have gone out. But even in that vast and lightless, degenerate era, there will still be structure. There will still be these dense, cooling, stellar corpses drifting through the dark. And there will still be the black holes, those we know of today, plus a great many more formed during the age of stars from the collapse of the largest suns. And over even longer, even more staggering timescales, these objects will themselves begin to decay, to disrupt, to come apart. Stars will occasionally wander too close to one another in the slow gravitational dance of the dying galaxies, and through these rare encounters, most of the dead stars will eventually be flung out into the intergalactic void, while a few spiral inward to merge with the central black holes. And there is another, deeper process at work as well. Many of our best theories of particle physics predict that matter itself is not truly eternal, that the proton, that humble particle which sits at the heart of every atom, of every star and planet and living thing, will itself eventually decay, will fall apart. Over timescales of perhaps 10 to the 34th years, or 10 to the 40th, or even longer, the protons making up the white dwarfs and the neutron stars and all the ordinary matter of the cosmos would slowly, one by one, disintegrate, causing these dead remnants to gradually evaporate away into a thin haze of lighter particles and radiation. Now, I have to insert a note of honesty here because it matters. Proton decay has never actually been observed. We have built enormous detectors deep underground, vast tanks of ultra-pure water surrounded by sensors, watching enormous numbers of protons, waiting for years to catch even a single one in the act of decaying. And so far, we have seen nothing, not one, which means that if protons do decay, they do so even more slowly than some of our theories had predicted. Their lifetime is at least 10 to the 34th years, and probably considerably longer. So this part of the story remains genuinely uncertain, an open question. But if proton decay does occur, as many physicists suspect it must, then all the ordinary matter in the universe, everything made of atoms, everything we have ever known or touched or been, will eventually crumble away into nothingness over these almost unimaginable spans of time. And so we arrive at the great question, what will be left after the stars have all died and gone cold? After the ordinary matter has decayed and crumbled into haze? After the galaxies themselves have dissolved and scattered? The answer, the remarkable answer, is black holes. The black holes will be the last great structure standing. They will outlast the stars, they will outlast the planets, they will outlast ordinary matter itself, outlast the very atoms. In the unimaginably distant future, the universe will be a vast, cold, dark, and almost perfectly empty expanse, containing little more than these isolated black holes, drifting in silence and darkness, separated from one another by enormous and ever-growing gulfs of expanding space, the final monuments, the last lonely citizens of a cosmos that once blazed with 100 billion stars. We sometimes call this the black hole era, and it is during this era, this long, dark, patient age, that our story finally reaches its climax. Because the black holes, too, you see, are doomed. We've known that all along, haven't we? Slowly, inexorably, with infinite patience, they radiate their mass away through Hawking radiation. By this point in cosmic history, the cosmic microwave background, that ancient afterglow of the Big Bang, which today keeps the big black holes warm and growing, has long since cooled to virtually nothing, stretched and chilled by the endless expansion of space until it is colder than even the most massive black holes. And so, at last, the evaporation proceeds unimpeded. The balance has tipped permanently, and the black holes are now losing more than they gain. They begin in earnest to die, one by one, over those vast time scales, 10 to the 67th years for a stellar mass black hole, 10 to the 100th years and beyond for the supermassive giants that once anchored the galaxies. The black holes shrink and heat up, and finally, in those characteristic explosive flashes of gamma rays wink out of existence, each one departing the universe in a final, brilliant, lonely burst of light. Imagine it. Try, if you can, to truly imagine it. A universe almost infinitely old, unimaginably vast and dark and cold and empty. An expanse so enormous, so stretched out by eons of expansion, that the few remaining objects are separated by distances that dwarf the entire size of the observable universe today. And in this vast darkness, the only events, the only happenings of any kind whatsoever are the occasional, isolated, widely scattered deaths of the last black holes. Here, a sudden flash of gamma rays, as some long-dead galaxy's central black hole finally completes its evaporation and explodes. And then darkness again for eons beyond counting. And then, somewhere else, unimaginably far away and unimaginably later, another flash, another death, each one a tiny, brief, lonely fireworks display in an endless ocean of black, each one separated from the next by gulfs of time so vast that they make the entire history of the universe up to now seem like less than the blink of an eye. The last black holes, dying alone in the dark, one by one, across spans of time that have no real meaning to any mind that has ever existed. And then, after the very last and largest and coldest of them has finally died, after perhaps 10 to the 100th year, a duration I cannot even pretend to make meaningful to you, or to myself even, these events cease. The last flash fades, and there is nothing left to happen ever again. And what remains then? After the final black hole has evaporated? After the last flash of light has faded into the dark? The answer is almost nothing at all. A thin, cold, impossibly dilute soup of photons and other stable particles, the very last of the Hawking radiation, mingled with whatever scattered electrons and stray bits of debris remain from the long decay of matter, spread thinner and thinner across an endlessly, relentlessly expanding space, every particle drifting ever farther from every other alone. No structure of any kind. No light in any meaningful sense, just the dying, stretching, reddening ghosts of the final photons. No events, no change, no history. Just a featureless, frigid, near-perfect emptiness approaching ever closer to a state of absolute maximum entropy, of perfect and final equilibrium, of complete and eternal sameness. Physicists sometimes call this the dark era, or simply the heat death of the universe. It is the ultimate fate predicted by our current understanding of physics, a cosmos that ends not with a bang, not with a dramatic collapse or a fiery cataclysm, but with the slow, quiet, patient, and utterly complete dissolution of absolutely everything into a cold and uniform and eternal nothingness. And here is the thing I most want you to hold on to, the point that ties this entire vast story together. The agent of that final dissolution, the very process that destroys the last structures in the universe, that erases the black holes which had outlasted everything else, that turns out the final lights of all creation, is the same process I have been telling you about from the very beginning. It is Hawking radiation. It is the slow eating of black holes by the quantum vacuum. It is quite literally the thing that extinguishes the last embers of the cosmos. The last meaningful act in the entire history of the universe, the final event before the eternal silence, is the evaporation of the last black hole. Nothing can stop it. Nothing can outlast it. Nothing can survive it. It is, in the most complete and literal sense imaginable, the end of everything. The quantum fizz of empty space, which we began with that tiny, restless trembling of the vacuum, turns out to be the force that has the last word. It outlasts the stars, the galaxies, the matter, and the black holes. It is the patient undertaker of the cosmos. Now, I realize, I really do, that this might sound, almost unbearably bleak, crushingly so, perhaps. The universe blazes with light and life for a while, for a brief and shining moment, and then everything fades, decays, evaporates, dissolves, and finally dissipates into a cold and lightless and eternal nothing. Over timescales so vast that a human life, a human civilization, the entire span of life on Earth, seems less than a single fleeting heartbeat in the lifetime of a single star. And I will not stand here and pretend to you that there is nothing melancholy in that vision. There is. Of course there is. To contemplate the final death of everything, the ultimate silence, the end of all light and all change and all possibility, it would be strange, I think, not to feel something solemn, something wistful in the face of it. But in part 3, our final part, I want to offer you a very different way of looking at all of this. A complete shift in perspective, because I do not believe, when all is said and done, that this story is truly a sad one. I have come to believe, after a lifetime of thinking about these things, that it is in fact a story of extraordinary, almost overwhelming beauty, a story of deep and unexpected unity in the laws of nature, of the most profound interconnection between the largest and smallest scales of reality, and of the almost miraculous, almost absurd fact that we tiny, fragile, fleeting creatures here, for the briefest imaginable instant, in the bright opening moments of the cosmos, are somehow able to understand any of it at all. I want to talk about what it truly means that the universe is comprehensible. I want to talk about Stephen Hawking, the man at the center of this story, and what his life can teach us. And I want to reflect, in the end, on what this whole grand narrative, from the quantum fizz of empty space all the way to the final death of the last black hole, reveals about our own place in the cosmos, and about the strange and precious and unrepeatable gift of being here, now alive and aware in the age of light. So, with the end of the universe now behind us, and the meaning of it all still ahead, so we'd arrived at this rather sweeping and, I'll freely admit, somewhat sobering vision. The universe blazing with starlight for a while, a brief and shining while, and then the long, long fade. The stars dying, the matter decaying, and finally the black holes themselves, the last great structures standing in all of creation, evaporating one by one through Hawking radiation until nothing remains but a cold, thin, featureless soup of particles drifting through an endlessly expanding darkness, the end of everything, brought about in the final reckoning by the slow eating of black holes by the quantum vacuum. And I promised you at the close of part 2 that I wanted to offer you a different way of looking at it all. So let me, try my very best to make good on that promise. Because I really do believe there is another way to see this. A truer way, perhaps. I want to begin with what I think is genuinely one of the most astonishing facts in all of human experience. And it is not this time a fact about black holes, or about quantum mechanics, or about the ultimate fate of the cosmos. It is a fact about us, about you and me. It is the simple, staggering fact that we know any of this at all. Think just for a moment about what we have actually done together in this conversation. We've talked about the death flashes of black holes that may be exploding right now, billions of light years away across the gulf of space. We've talked about events that will not unfold for 10 to the 100th power years into the future in a cosmos so old, so utterly transformed, that nothing we could possibly recognize will remain within it. We've talked about the quantum fluctuations seething in empty space, about particles far too small and far too fleeting to ever be directly seen, about the precise temperature of an object from which not even light itself can escape. And we have done all of this From where exactly? From a small, wet, rocky planet orbiting a thoroughly ordinary star, tucked away in the unremarkable suburbs of one fairly average spiral galaxy, among hundreds of billions of other galaxies scattered across the observable universe. We are, by any conceivable measure of cosmic scale, almost nothing less than specks. Specks upon specks upon specks. Here for the merest eye blink of cosmic time, and then gone. And yet, we have figured this out. Using nothing but observation and reason and mathematics and the strange soaring power of human imagination, we have reconstructed the entire history of the cosmos, reaching all the way back to its first fraction of a second. And we have projected its future forward to the very end of time. We have weighed black holes we will never touch. We have calculated the temperatures of objects we will never visit. We have predicted the behavior of the universe across spans of time that dwarf our own existence into utter insignificance. We have, in a very real and very literal sense, held the entire universe, its birth, its long life, and its distant death inside the 3-pound organ of soft tissue that sits between our ears. We have taken the cosmos into our minds and understood it. I find that, almost overwhelming when I truly stop and let myself feel the weight of it. And it becomes all the more moving when you consider the man at the very center of this whole story, Stephen Hawking. Because Hawking did much of his greatest work, including the discovery of the radiation that bears his name. The very thing we spent all this time exploring while confined to a wheelchair, his body progressively failing him, gradually robbed by disease of the ability to move, and eventually even of the ability to speak, until he could communicate only through a computer, painstakingly selecting words one at a time, letter by letter, with the twitch of a cheek muscle. And from within that profoundly, almost unimaginably limited physical existence, a body that had become a kind of prison, every bit as confining in its way as any black hole, his mind ranged freely, gloriously, across the entire cosmos. He worked out that black holes glow. He uncovered a deep and previously unsuspected connection between gravity, quantum mechanics, and the science of heat, a connection that nobody before him had even glimpsed. He saw further, in some real sense, than almost any human being who has ever lived. And he did it through the sheer indomitable power of human thought alone. If you ever wanted proof, real, undeniable proof that the human spirit is not in the end defined or confined by the limits of the body, then there it is. There it is in the life and work of Stephen Hawking, the frail body and the boundless, soaring mind. So when we contemplate this vast and ancient and ultimately dying universe, I think the very first thing we ought to feel is not despair, not bleakness, not a sense of our own smallness or futility. I think the first thing we ought to feel is a kind of astonishment, a deep and grateful astonishment at our own extraordinary capacity to comprehend it. Because here is something that I think is easy to overlook, easy to take for granted, but that is, when you really consider it, perhaps the deepest mystery of all. The universe is not obligated to be understandable. There is no law written anywhere that says a species of curious primates who evolved on the African savanna to find ripe fruit and to avoid hungry predators should be able to grasp the quantum structure of the vacuum, or the thermodynamics of black holes, or the ultimate fate of all things. And yet, somehow, against all reasonable expectation, we can... Albert Einstein himself once said that the most incomprehensible thing about the universe is that it is comprehensible. And I think that is exactly, profoundly right. The deepest miracle is not merely that the universe exists. It is that the universe makes sense. That it follows precise elegant, discoverable mathematical laws, laws that our minds, these improbable arrangements of atoms, are somehow able to uncover and to understand and to find beautiful, that the cosmos is, in the end, intelligible to us, that we can read its story. That, to me, is the real wonder. That is the thing that ought to take our breath away. Now, let me turn directly to the question of the ending itself, to this vision of cosmic death, of everything dissolving into a final cold nothingness. Because I want to push back, gently but firmly, on the instinct to find it simply depressing. I want to give you some reasons why I think that instinct, while entirely understandable, may be leading us astray. First, there is the matter of the timescales, and I think this is genuinely critically important for keeping our perspective. The numbers we have been throwing around so casually, 10 to the 67th years, 10 to the 100th years, these are not just large numbers. They are large in a way that fundamentally totally breaks our intuition, that shatters any attempt at comparison. Let me try one more time to convey this, because I don't think it can be overstated. The current age of the universe is about 14 billion years. That already feels incomprehensibly, dizzyingly long. It is roughly 3 times the age of the Earth and 100,000 times longer than our entire species has existed. But the lifetime of a stellar mass black hole is 10 to the 67th years. If you wanted to express the relationship between those two durations, you would find that the universe, in its entire history so far, has lived through only the most infinitesimally tiny sliver of the time it will take for even one such black hole to evaporate. The universe would have to age by a further factor of 10,000 trillion times its present age before that black hole even finishes its slow dissolution. Here is another way to try to feel it. Suppose we compress the entire current age of the universe, all 14 billion years, the whole sweep of cosmic history, from the Big Bang to this very moment, down into a single second. One tick of the clock. On that compressed scale, where all of history so far is just 1 second, how long would it take for a supermassive black hole to evaporate? The answer is that it would still take vastly, vastly longer than the current age of the universe, even measured in those compressed seconds. We are so unimaginably, so absurdly far away from these endings that they are, in any practical or even emotional sense, completely and utterly irrelevant to us and to any conceivable future we might care about. The heat death of the universe is not something to lose any sleep over. It is not a looming threat. It is so remote, so impossibly distant, that the very word remote doesn't begin to do it justice. It lies beyond the horizon of any meaning the human mind can attach to time. And what that profound remoteness means is something rather wonderful when you turn it around. It means that we are living right now, you and I, in this very era, in the most spectacular, the most eventful, the most luminous age that the universe will ever have, the age of light. The stelliferous era, the brief, brilliant, glorious opening chapter while the cosmos is still young and full of fire, when there are stars to warm the worlds and light to see by and structure to marvel at least here on this one small planet, life to wonder at it all. From the perspective of the entire near-infinite lifespan of the universe, we have arrived at the grand celebration at the perfect moment, while the lights are still blazing, while the music is still playing, while the stars are still being born and still burning bright. The long darkness is indeed coming. But it is so unfathomably far off that we and our descendants, for an almost limitless span of future generations, get to enjoy the whole magnificent show. We are not, you see, latecomers shuffling into a dying and emptying cosmos. We are early. We are among the very first. We are here in the golden age of the universe, the springtime of all things. And there is, I think, something genuinely glorious in that realization. Something to celebrate, not to mourn. Second, I want to reflect a little more on the deeper meaning of the unity we've uncovered in this story, because I think it is, in its own way, a source of real consolation and real wonder. The thing that destroys black holes, this Hawking radiation, is not some arbitrary, isolated quirk of nature, some random fact with no larger significance. It is, as we've seen, the one place in all the cosmos where our two greatest theories, general relativity and quantum mechanics, reach out across the divide and actually touch one another. It is a bridge between worlds, a clue, a precious golden thread that physicists are even now following with great excitement toward what we hope will someday be a final and complete understanding of nature. A unified theory of quantum gravity that would weave everything together, gravity and the quantum, the very large and the very small, into a single, seamless, coherent whole. And isn't that, when you think about it, a rather marvelous thing? That by studying how black holes die, this seemingly morbid, seemingly esoteric subject, we are led, step by step, toward the very deepest laws of reality. That the slow evaporation of these objects, so utterly removed from anything in our daily lives, turns out to be one of our single best laboratories for probing the ultimate nature of space and time and matter and information. The information paradox I described to you in Part 2 has driven some of the most profound theoretical advances of the last several decades, revealing wholly unexpected and deeply beautiful connections between gravity and information, between the geometry of space-time itself and the quantum entanglement of distant particles. We are discovering, even now, even as we speak, that reality is far stranger, far more subtle, and far more deeply interconnected than we had ever dared to imagine. And the dying black hole, that lonely evaporating object in the cold of space, is, in a very real sense, our guide and our teacher, leading us ever deeper into that strangeness, that beauty, that profound interconnection. I want to pause here and acknowledge something, because intellectual honesty demands it. Everything I have told you about the far future of the universe, the heat death, the evaporation of the last black holes, the final cold silence rests on the assumption that the laws of physics as we currently understand them will continue to hold, unchanged, across those almost infinite spans of time. And that is an assumption, a reasonable one, our best current guess, but an assumption nonetheless. The truth is that our understanding of the deep future is far from complete, and there are genuine uncertainties, genuine open questions that could change the picture in dramatic ways. Consider dark energy, for instance, that mysterious force that is currently causing the expansion of the universe to accelerate. We do not know what it is. We do not know whether it will remain constant forever or whether it might change over time. If it stays constant, we get the cold, gradual heat death I described. But if dark energy were to strengthen over time, the universe could end far sooner and far more violently in what some physicists have called the Big Rip, a runaway expansion that would eventually tear apart galaxies, then stars, then planets, and then atoms themselves. Alternatively, if dark energy were to weaken or reverse, the expansion could halt and reverse, leading to a big crunch, a collapse of the entire cosmos back in upon itself. We simply do not yet know which of these fates awaits us. The death of the black holes by Hawking radiation is the most likely scenario given what we currently understand, but the universe has surprised us before many times over, and it may very well surprise us again. And there is an even stranger possibility, one that touches directly on the quantum vacuum we've been discussing all along. Some physicists have raised the question of whether the vacuum of space, the very ground state of reality, the lowest energy configuration of all the quantum fields, is truly stable, truly final, or whether it might be merely metastable, a temporary resting place, lower than its immediate surroundings, but not the lowest possible state of all. If that were the case, then somewhere, at some point in the vast future, a tiny bubble of true vacuum could spontaneously form through quantum tunneling and then expand outward at the speed of light, rewriting the very laws of physics within it as it grew. This is the idea of vacuum decay, and it is, I'll freely admit, a genuinely unsettling thought. But here too, honesty requires me to add the crucial caveat. Our best current measurements suggest that even if such a process is possible at all, its timescale would be so enormous, far longer even than the evaporation of the largest supermassive black holes, that it poses no practical concern whatsoever. Not for us, not for our descendants, not for any conceivable civilization. I mention it not to alarm you in the slightest, but simply to convey to you how much genuinely remains open, how much remains uncertain and undiscovered at the very frontiers of this science. The story of the universe's ultimate end is, in truth, still being written. And that, I think, is itself a kind of gift, because it means there is still so much for future generations to discover, so many deep and beautiful questions still patiently waiting for their answers. The book of the cosmos is not yet finished. The final chapters are still blank, still waiting for minds not yet born to fill them in. There is a beautiful irony at the very heart of all this, one that I keep returning to again and again because I find it so quietly profound. The black hole, as I said at the very beginning of our journey together, is the ultimate symbol of doom and of permanence and of absolute inescapability. Nothing gets out. It is the perfect prison, the one-way door, the absolute and final end of all journeys. And yet, and here is the irony, the exquisite cosmic joke, the very same laws of physics that make it such a perfect, inescapable trap, also, in the end, guarantee its complete destruction. The escape that no particle trapped inside can ever achieve is ultimately achieved by the black hole as a whole. It escapes its own existence. It dissolves, particle by particle, back into the radiation and the quantum vacuum from which all things first arose. The prison and the liberation, the trap and the release are written into the very same equations, flowing from the very same mathematics. The most permanent object in all the universe is, when you look deeply enough, when you follow the logic all the way down, profoundly and unavoidably impermanent. There is a kind of poetry in that, a kind of deep structural poetry woven into the laws of nature themselves that I find genuinely, almost achingly moving. Nature contains its own opposites: creation and destruction, holding and releasing, birth and death, all bound together, inseparable in the same beautiful and economical mathematics. And maybe, just maybe, there is even a lesson hidden there, a lesson about impermanence in general that reaches beyond physics and into our own lives. We tend, naturally, to think of the things around us as solid and lasting and permanent. The mountains, the oceans, the stars overhead, the very ground beneath our feet. But the deepest lesson of physics, repeated at every scale we examine, is that nothing at all is truly permanent. The mountains erode, grain by grain, into the sea. The stars burn through their fuel and die. The continents themselves drift and collide and reshape over the ages. And even the black holes, the most durable and enduring things in all of creation, the last survivors of the cosmic story, eventually fade away into the dark. Everything is in flux. Everything is temporary. Everything is part of a vast, slow, ceaseless, and magnificent process of transformation and renewal. And rather than finding that thought frightening, or saddening, I think we can, if we choose, find it strangely liberating, because we are part of that process too. We are not separate from it, not exiles from the cosmos looking in. We are woven into its very fabric. The atoms that make up your body, every single one of them, were forged in the nuclear furnaces of ancient stars that lived and died long, long before our sun was even born. The carbon in your cells, the oxygen filling your lungs at this very moment, the iron coursing through your blood, the calcium in your bones, all of it, every atom was cooked in the bellies of stars and then scattered across space when those stars exploded in their death throes, seeding the galaxy with the raw material of worlds and of life. We are, quite literally, and not at all metaphorically, made of stardust. We are the ash of dead stars, gathered up by gravity and arranged through some 4 billion years of patient cosmic evolution into a form that can look back up at the night sky and understand where it came from. We are the universe's own material, briefly, improbably organized into something that can know itself. And that, I think, leads us to the single most important question of all. The question that lies at the very end of this long road we've traveled. In this entire grand narrative, from the quantum fizz of empty space, through the blazing birth and death of stars, to the final lonely evaporation of the last black hole, where, in all of that, does meaning come from? Where does it live? Not, I would suggest, from the cosmos itself. The universe, considered purely as a physical system, is indifferent. It is governed by impersonal laws, grinding forward according to mathematics that care nothing for us, heading inexorably toward a cold and silent and lightless end. The universe does not provide meaning. The meaning, I have come to believe with all my heart, comes from us. From conscious beings, beings capable of love, of curiosity, of wonder, of grief and joy, and understanding who, for one brief and shining moment in the immense and overwhelming sweep of cosmic time, get to be aware, who get to ask questions, who get to look up at the stars and feel that catch in the chest, that sense of awe, that reaching towards something vast and beautiful and beyond ourselves. The universe, for the overwhelming majority of its existence, both the long ages already past and the unfathomable ages still to come, will be dark and cold and dead and empty. But for this brief, glorious, improbable window, the window that we just happen to inhabit, against all odds, it has produced something utterly extraordinary. It has produced itself made conscious, matter that contemplates matter, atoms that ponder atoms, a cosmos that has, through us, and quite possibly through countless other minds, scattered across the galaxies that we have not yet met, become aware of its own existence and of its own beginning, and even of its own eventual end. And to me, that does not make our existence feel small or pointless or futile against the immense backdrop of cosmic death. Quite the opposite. It makes it feel precious, almost unbearably, achingly precious, because it is so rare and so fleeting and so utterly, wildly improbable. Just think about it. Really think about it. You are a collection of atoms, ordinary atoms, the same carbon and oxygen and hydrogen found in stars and comets and interstellar dust that has become arranged through nearly 14 billion years of cosmic evolution into something that can understand Hawking radiation, that can grasp and hold in its mind the ultimate fate of the entire universe. That can be moved to tears or to laughter or to awe by the sheer beauty of a mathematical equation, or by the sight of stars on a clear, dark night, or by the strange and wonderful idea that black holes glow faintly in the dark and slowly, patiently die. That particular arrangement of atoms, that improbable, temporary, miraculous arrangement, that is you. That is all of us. And it will not last forever. Not for you as an individual, not for our species, not for the cosmos as a whole. We are all, every one of us, and everything we have ever known, temporary arrangements of stardust, here for a moment and then gone. But the fact that we exist at all, even for this brief instant, even against the certainty of our own ending, that to me is the single most remarkable and most beautiful thing I know of in all of physics, in all of existence. So when I tell you that something is eating black holes across the universe, and that it's spreading, and that nothing can stop it, all of which is, as we've seen, entirely and rigorously true. I do not want you to hear, in those words, a story of doom. I do not want you to come away from this feeling diminished or frightened or filled with cosmic dread. I want you to hear instead a story of profound and unexpected and almost unbearable beauty. A story in which the very same quantum principles that fill the empty vacuum with fleeting, flickering virtual particles also, over spans of time beyond all imagining, dissolve the most powerful and permanent objects that the universe has ever produced. A story in which the largest scales of nature and the smallest scales of nature, the cosmic and the quantum, the black hole and the vacuum fluctuation, turn out to be woven together inseparably into a single, coherent, and breathtaking tapestry. A story in which even endings, even death, even the final silence of the cosmos are revealed to be part of a deeper order. An order so elegant, so beautiful, that our minds, astonishingly, miraculously, are able to perceive it and to follow it and to understand it. The black holes will die, yes. The stars will fade and go cold. The matter will decay. The universe will, in the fullness of an almost endless time, grow dark and silent and empty. All of that is true, and I will not pretend otherwise. But not for an almost inconceivably long time. And in the meantime, in this vast and precious meantime that is our home, here we are, conscious, curious, alive, awake, in the age of light, beneath a sky still crowded with stars, on a warm and living world, able to ponder the very deepest questions that the cosmos has to offer, and able, what's more, to find joy in the pondering. That, to me, is not a cause for sorrow. It is a cause for the deepest gratitude and for wonder, and for a kind of quiet, fierce joy, the joy that comes from understanding even just a little our true place in this vast and beautiful and impermanent universe.